Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to provide examples of how to draw free body diagrams and how to apply Newton's second law. So let me describe a little bit about what we're going to be chatting about here. So imagine we got these three boxes, I guess, and they're relatively large boxes at 25 kilograms apiece. So I put mass A equals mass B equals mass C, 25 kilograms, meaning that the total system here would have a mass of 75 kilograms. And this person here, Bob maybe, walks up and applies a 200 Newton force. And we observe that the system, this whole kit and caboodle here, accelerates to the right at 1 meter per second So we're going to look for a couple of things. One, we're going to try to calculate a frictional coefficient between these two surfaces. And second, we're going to try to calculate the normal force that exists between box B and C. Now, if you're watching this video, don't let the details here get in the way of learning here. Pay attention to the process of how this thing's being analyzed, because pretty much regardless of what these details are, how we're going to analyze it's going to be very, very similar. Now, drawing free body diagrams. When you draw free bodies, the first thing you have to do is define your system, what's called sometimes your system of interest. And there's lots of free bodies we could draw here. We could draw a free body of mass A, or maybe B, or a free body of C. These are all decent free bodies to draw, or we can draw a free body of B and C together. Oops, go backwards. What I'm going to do is I'm going to start with a free body of the entire system. That's one of the tricks here, is knowing when to look at the details, like break it apart, and when to look at the system as a whole. And I think this would be a good place to start, because we know a total mass, we know the acceleration of the system, and we know this external force. So I'm going to draw a free body of the entire system here, the whole thing. Or let me restate that. I'm going to define all of this as my system. Now, when you draw free body diagrams, I think it's very good physics to not try to put your force vectors in the original picture. I like to, whenever possible, redraw the system however I'm defining it, and then start putting force vectors in. And I guess the first one I'll put in here, let's put that 200 Newton force in here. And I see that I put that system a little higher. All right, that's all right, I'll just do this. So the force vector is applied right here. You can still almost see the guy's hand and imprints here. That 200 Newton force vector would go here in this picture. Now, you have freedom left or right. I could draw this thing over anywhere along this path. Remember, force vectors have what's called a line of action. But you do want to draw it where it's actually applied in the other direction. Here's what I mean. That force vector is applied right here on the system, so you don't draw it down here or up here. So in this particular case, you have freedom left or right where to put it, but not up or down. Now, how do I label it? I could label it 200 newtons, or I could label it just F, because I've said right here that F is equal to 200 newtons. Either one is just fine. Now, other forces. You can put individual gravitational force vectors on, and I could draw 3 of them, or I can just draw one force vector. It's just fine for this example, down. And that force vector actually is quite a bit larger than this. Let me talk about magnitudes here. The whole system is 75 kilograms. That's going to make that force vector equal to roughly 750, a little less than 750 newtons. So it should be quite a bit longer than this one. So I think what I'll do is we'll just draw it like this. Right, we'll put mg, where that mass is equal to 75 kilograms. I think what I'll do is just shorten this force vector up, because again, I know that this one is quite a few times larger than this one. It's not important that I get it ratio, like exactly right ratio-wise, but in this example, this force vector is quite a bit larger than this one, so your free body should demonstrate that. Okay, next force, and I'm going to take this entire thing here and move it down to give myself more room. Okay. All right. Surfaces in contact along here, that's going to create what we call normal forces, and really there's 3 of them, like one on surface, the bottom of A, one on the bottom of B, one on the bottom of C. It's pretty common to take force vectors like that, group them into one single force vector, draw that up, right? And that's what we call a normal force. And again, this one would equal the normal on A plus the normal on B plus the normal on C added together. And these three things, I'm referring to the vertical normal forces that are acting along this surface, and this surface. Now, if this was the only force and it were 200 newtons, and you write out Newton's second law, force equals mass times acceleration, and I start putting in numbers, this is 200 newtons equals 75 kilograms times A. If you solve this for A, you're going to get a number larger than 2. And you'll notice the observed acceleration in this example is 1 meter per second per second. So that's telling us there's another force in this free body, and that force is to the left. And that is a frictional force. So when you have surfaces in contact like this, you have two possible forces, vertical or normal forces and tangential forces. The normal forces will just about always be there. The tangential forces depend on the nature of these surfaces. And the tangential ones are what we call the frictional forces. So I'm going to go ahead and put a frictional force in this picture. And this really is the sum of three frictional forces. Some of that is acting along A, some of it along B, and some of it along C. Oops. It is not necessary when you draw these free bodies and label these to go this far and talk about the detail here of this, but I'm just doing it because it's a video intended to help teach people how to do this stuff. All right, so now that we have our free body, now what we can do is we apply Newton's second law, which says the net force acting is equal to mass times acceleration. I'm going to go ahead and write that out here. Net force equals ma. Newton's second law is a vector law, and that means it gets applied by direction. There's two equations I can write for this free body. One, if we add up forces in the y direction, they're going to add to 0, calling up positive. Now, y 0, there's no way that this system is going to accelerate this way. There's not going to be an acceleration in that direction, so we know that the net force in that direction is 0. And we look at our free body to write the equation. We've got the normal up, the mg down, and again that force vector is down, so minus, and then equals 0. So our normal force, this one right here, I have now calculated at is equal to mg. That's going to be 75 kilograms times 9.8 meter per second per second. Let me go ahead and take a moment and get a value out of that. I get 735 newtons. Now let's look at the horizontal direction. Right? The other thing we can say about this free body here is if we add up the x components of these forces, and I'm going to go ahead and call right positive, they have to equal ma. Now, my standard rule of thumb, I call these carrots, Captain Rod's rules of thumb. Identify the acceleration direction, call that positive. This system's accelerating to the right, so I'm going to go ahead and call right positive. And then we look at our free body to write the equation. Here are two forces, both in the x direction. One is to the right, the other to the left. And I think what we can do here is actually, we have values for this and the entire right-hand side, so we can find the frictional force here. So let's go ahead and do that. F minus ma is equal to the frictional force if we move this to the left and this to the right, and this is 200 newtons minus 75 kilograms times 1 meter per second per second, and that frictional force I get, oh, I don't need a calculator for that, 200 minus 75, 125 newtons. So our frictional force, I'm going to go ahead and just store these over here, 125 newtons acting on this system. All right, at this point we're actually ready to answer one of these questions here. What was the frictional coefficient? So this is a sliding frictional force. The sliding frictional force is equal to the coefficient of sliding friction times the normal. I'm just going to put the coefficient of friction and not worry about the sliding part. And we calculated the frictional force at 125 newtons, and the normal force at 735 newtons. So our coefficient of friction is 125 over 735, 0.17. Now, frictional coefficients, again, that's a dimensionless quantity because we're taking Oops, I have that on the wrong side of the equal sign. Sorry about that. Hopefully I said it right. Frictional force is equal to the coefficient of friction times the normal. All right, and the math is okay. 125 over 735 is 0.17. Frictional coefficients are, they're just decimals. They're percentages. This just means that the frictional force, the sliding frictional force, is going to be 17% of the normal force. All right, so we got this one knocked off. We know about that. All right, normal between B and C. So in my original picture, that's the normal force between these surfaces right here. Probably green is not the best color to use there, but it's the normal between these surfaces. There's a couple different free bodies I can draw here to get that normal. I could draw a free body of just this. I could draw a free body of this part of the system. That would do it as well. I'm going to go ahead and draw a free body of just mass C. So again, I'm going to clone it. A lot easier to do with these computers than on paper, but bring that over here. All right, start putting force vectors in. First force vector I usually think of is the gravitational force vector. That is down, equal to mg. Oops. Now this mass really is just mass c, so I'm going to put a mass c times g. This mass, you'll notice I drew it like a large M. That's all of them. I drew this vector shorter because it's roughly 1/3 the length of this. All right, looking at an original picture, here's an upward normal force. That's the normal I'll call on C, between the ground and C. We are going to have a normal force between those two, which is going to be, again, if you look at this surface, the normal force between these boxes is to the left on this animal, to the right on this animal. So that's going to be a force in this direction. And how about we call that normal BC for the normal between boxes B and C. Surface and contact again. So here we have we've already gotten the normal force, but we also have a tangential force, a frictional force there. That's the frictional force acting only on C. Can't really label it F because I used F here for the entire frictional force acting along all three surfaces. This is just on this mass C, and it's got to be quite a bit shorter than this guy. Maybe I'll go back and shorten that force vector up a little. Good enough. So force on C. And that's it. I can't think of any other important forces that we should put in the free body. So now it's a matter of writing the Newton's second law equations. Typically when you're dealing with friction, you will usually need the normal force. So I'm going to go ahead and write a force equation in the upward direction here. Sum of all forces, I'll call that the y direction, is equal to 0. This thing's not accelerating up. And I'll go ahead and call up positive. Why not? So we got this force vector minus mass c times g, and there are no other forces in the y direction, so equals 0. Normal c is equal to 25, I'll just do this, 25 times 9.8 in newtons, right, because kilogram meter per second squared works out to a newton. 245 newtons. All right. X direction, sum of all forces. X direction is equal to mass times acceleration. This thing is accelerating to the right. Now, I don't mean to imply that just because this is an X, there's going to be an acceleration. In this particular problem, I'm calling, right the X direction, up the Y direction. And this object is accelerating in this direction. So that's why this one has an MA and this one has a 0. In other problems, maybe something would be accelerating upward, and then you'd have an MA in the Y direction and maybe a 0 in the X direction. Okay, that'll change problem by problem. Right, to write our force equation, we look at our free body. We got to get this force to the right, normal BC. This force to the left equals MA. I'll put a little m times A. Now, this frictional force we can calculate because The coefficient of friction, there's probably no reason to believe it changes from surface to surface. We calculated a value, 0.17, so the frictional force should be 0.17 times 245. 245 is the normal force along the surface. I get 41.7 newtons. I'm just going to round that to 42 newtons for this example. All right, putting values in now. Normal BC is going to equal, adding this to the right, 42 newtons plus m, 25 kilograms, times a, 1 meter per second, and we end up with 42 plus 25, 67 newtons it's looking like. Just going to double check my math on that. 67 newtons. Okay, we're good. Just making sure. I haven't had a lot of coffee today, so. All right, I think we're pretty well done with this example. Again, the idea was how to draw free body diagrams and use Newton's second law. In this case, we started with a free body of the entire system. That's this animal. This 200 newtons is applied to that part of the system. Wrote our Newton's second law equations for that system. And those were like here and here. Next part, we drew a free body of just mass C. And again, that was by choice. We could have also done like A and B together. An important thing I should point out is you'll notice that the 200 Newton force here that this person is applying did not show up in this free body. And that's because that 200 Newton force is applied right here. And that person is not in contact with mass C. Now, the 200 newtons does make the whole system start accelerating right, and it creates normal forces here and here. But a free body of mass C does not have the 200 newtons applied, nor does a free body of mass B. Only a free body of A, or maybe A and B together, or A, B, and C together. But any other free bodies would not have that 200 newtons applied to it. So I see this video is getting a little on the long side here. I think I'll just stop it right there. I hope it helps. Have a great day.